Okay, now let's look at some parameters of the binomial distribution. If a count of x has a binomial distribution with number of trials n and probability of success p, the mean and standard deviation of x are as follows. So again, we'll take the mean, which is the mu of x. This is found by the formula by taking the number in the trials and multiplying them by the success rate. So that's our mean, otherwise known as our measure of center. And then our spread, or our standard deviation here, is going to be the square root of the number of trials times the probability of success times the complement of the success. So that's going to be our spread. And in order to find the shape, we would just plot these and look at the histogram or whatever graphical representation we choose here. But again, we always want to comment on our center, shape, and spread. So we at least have a mathematical way to find the first two elements here. So these are formulas that will be provided to you on the AP Stats formula sheet, so you do not need to memorize them. They're very simple here, but alas, don't stress out about the notation. You will always have your formula sheet to reference. So let's take a look at some examples here. Alrighty, so Mr. Pinto's 42 AP Statistics students performed an in-class activity involving telling the difference between tap water and bottled water. If we assume the students in his class cannot tell tap water from bottled water, then each has a 1 in 3 chance of correctly identifying the different type of water by guessing. Let x equal the number of students who correctly identify the cup containing the different type of water. Let's find the mean and the standard deviation of x. Alright, so first thing here, let's look at the setting, right? Because this is just probability. Is this successive independent events? Is this mutually exclusive? Are these independent? Would I look at a two-way table? Do I need a probability tree diagram? Was I given any conditional information? I was not given much of this, so I'm going to look for a setting, because I don't immediately off the top of my head recognize that what type of probability this might be. So let's look at the settings here. So I'm noticing that they have to tell the difference between tap and bottled water. So if we assume the students in this class cannot tell the tap from the bottled water, this is a binary outcome, right? Either they can or cannot tell the difference, right? That's our success. We could assume these are independent because each student would have their own results. So own results per student. I'm just shorthanding here. But we're going to imagine that the first student has no influence on the 27th student, who has no influence on the 42nd student. I look here, and my sample size, or actually my population really, would be 42. I have 42 students that are enrolled in Mr. Pinto's AP Stats class. And then the last one would be the probability of success, and here that's about a 1 in 3 chances of correctly guessing. So because we've got bins here, we know that x is most likely a binomial random variable with the following characteristics: a sample size of 40 and a success rate of 1/3. And now because I know this, I can use my parameter formulas from the previous page to find these values. So if I wanted to find the mean, again, what am I looking for? What does it mean? Here it's NP, and then what does it look like with the value substituted? And what does it equal? So here, the mean, so let x be the number of students who correctly identify the cup containing the different type of water. We would expect the average to be, is it 7? It's not 7, LOL. It is 14, and then what's our context here? It would be about 14 students. So again, 4 parts that we're looking for. What parameter, or which probability? What's the formula? What is the substitution? And then what is the work in context? So 4 parts, really 5 with the context piece here. But then we can also do this for the standard deviation. So again, what am I looking for? What does it mean? What does it look like? So I'm going to do 42 times 1/3 times 2/3. And this is going to give me approximately 3.06 students. So here in the long run average, we'd expect about 14 students to correctly guess the different types of water. In the long run average, the number of students differs from the mean by about 3.06 students who can correctly identify the water. So not too shabby. Again, interpretations, context, and our distribution. And then let's make sure you're set up for success on the following example. A company owns 400 laptops. Each laptop has an 8% chance of not working. You randomly select 20 laptops for your salesperson. And then we have a few situations. So again, we would check here what the scenario is. Is it binary? Well, it looks like either the laptop does or does not work. Is it independent? Yeah, we could assume that one laptop would have no influence on a separate owner's laptop. Is there a fixed amount of trials? Well, our company owns 400 laptops in our population, but we have randomly selected 20, so we have an SRS here, or however we selected these 20, but it's fixed here at 20 laptops. And then the probability of success, and again, success doesn't mean always a good thing. Here, the success is the probability of not working. But again, we see that we have this bin situation, so we are going to say that X is binomial with the following parameters. We have 20 for our n, and then we have 0.08 for our probability of success. And our sample space is going to look something like, I don't know why I've gotten into the practice of drawing the lines, so you can just list them out. So we've got 0, 1, 2, all the way up to 20. That will make up our sample space here. So for example, in part A, it says, what is the probability that exactly 5 will be broken? Okay, so exactly 5, this is back to probability. I have 20 laptops, I choose 5 of them. That would mean that 8% would be broken, and about 92% would not be broken. And not necessarily would be broken, but we'd expect to be broken, you know, all those nuances. So find that probability. In the second one, what is the probability that all 20 will work? So the probability that all 20 will work here, and actually this would be the probability that exactly 20 will work. So I've got to rewrite this statement here. So the probability that all 20 will work, okay, so if all 20 work, that means from number 1 up to number 20, those are all working. Well, who's left out when I do this? Number 0. So the probability that all 20 work is the same thing as saying 1 minus the probability of none of them working. And so again, we'll look at this as the following. So we would just set up our situation here, and then let's see, 0.92 to the 20. Probability that none of them fail to stop working would look something like this, and so then you could find this answer. And then lastly, of course, our parameters. So find the mean, we would do NP. So how many would we expect to not work? And then for our sigma, same thing, NP times 1 minus P. We'll take the square root of that. So these are just some examples of ways you might see the binomial distribution on a few multiple choice questions. So hopefully you've been set up for success up to this point. Go ahead and find your probabilities, and then we'll do some in-class comparison.